Bismillahirrahmanirrahim. Assalamu alaikum, students. Today, my topic is first the temperature entropy diagrams. Remember that entropy, which we denote by letter S, is a state function. It is a state function. Temperature is a state function, right? Now, we know that we use PV diagrams for PVT systems. PVT systems, that means those systems where we can use these three macroscopic variables to specify a thermodynamic state or equilibrium state of a system, like we talk of constant, mass, gas systems. Now, since entropy is also a state function, so we can add S to this list also. So as we can use PV to specify a state, we know any point in PV diagram represents a thermodynamic state, a thermodynamic state, or which we call equilibrium state. Similarly, we can use entropy temperature diagrams, and each point on entropy temperature diagram represents a thermodynamic state or equilibrium state, right? Now I will first draw the entropy temperature diagram for a Carnot cycle. Let me use the next page. So what we do, we take temperature on y-axis like this, and entropy on x-axis. So this is my temperature axis, T, this is my entropy axis. Then let me label the point, or I will first find the diagram. So my diagram will be like this. So I label the points. Let this be point 1. Let this be point 2. Let this be point 3. First I will draw. You draw with me. Then I will explain. And this is the temperature entropy diagram of a Carnot cycle. Then I will explain it. What it, let me name it. Figure 1, it represents the temperature entropy diagram of a Carnot cycle, right? Let me compare it with the PV diagram. Remember the PV diagram of a Carnot cycle. It's like this. Let me use another color here. Let me complete it first. So this is my point 1. This is my point 2. This is my point 3. This is my point 4. So this is, let me name it figure 2. It is the PV diagram, that is pressure, volume, PV. This is TS, temperature, entropy. So it is pressure, volume diagram of a Carnot cycle, right? Remember, we have explained this cycle already. What is happening? Let me use this space, small space here, and another color. So from 1 to 2, we have isothermal expansion, right? From 2 to 3, we have adiabatic expansion, right? From 3 to 4, we have isothermal compression, and from 4 to 1, we have adiabatic compression. We have already done it. I'm just reminding you in order to compare PV diagram with the TS diagram, that is temperature entropy diagram. So first we have isothermal expansion, that is from point 1 to point 2. So the temperature of the system stays constant. So in TS diagram, 1 to 2 step will be like this. Since the temperature stays constant, it will be a horizontal line. T stays constant, and that T is which T? From 1 to 2, temperature of the system is same as that of the hot reservoir, so which we represented by TH. So from point 1 to point 2, the system is in thermal contact with the hot reservoir, and we know it absorbs heat from the hot reservoir. Temperature of the hot reservoir is TH, right? And another thing you need to remember here, entropy is increasing from point 1 to point 2. So let me name this entropy here at, again write this TH as T2 also, and entropy at point 1 S1, entropy at this point S2, right? So from point 1 to point 2, the system is in thermal equilibrium with the hot reservoir. It absorbs heat from the reservoir, and the process is reversible. And we know the change in entropy ds is what? Is dq by t, right? dq is the heat absorbed by the system reversibly. T is the temperature. So since heat goes into the system from point 1 to point 2, so change in entropy is positive. Entropy of the system increases from point 1 to 1.2, from S1 to S2, right? And this change occurs at the temperature TH, or which we call now T2. Then at point 2 to point 3, what happens? There is an adiabatic expansion taking place. So in adiabatic expansion, there is no heat exchange between the system and the surroundings. Therefore, change in entropy is 0. That means from point 2 to point 3, entropy of the system stays constant. So you can see from point 2 to point 3, as our system moves, entropy is not changing. Its entropy is remaining constant, S2. Right. Then from 3 to 4, we have isothermal compression. So what is happening? From 3 to 4, temperature of the system is same as the temperature of the cold reservoir, right? Because it is in thermal contact with the cold reservoir. So 3 to 4, the temperature of the system is Tc, temperature of the cold reservoir, which we call now T1, right? So what is happening to the entropy of the system from 3 to 4? Entropy is decreasing because heat is being rejected by the system to the cold reservoir. So dq is negative, so change in entropy is negative. So entropy of the system decreases from S2 to S1, from point 3 to 4, right? Then from 4 to 1, we have another adiabatic compression. So again, the system is adiabatically isolated from its surroundings. So there is no heat exchange taking place between the system and the surroundings. So entropy change is 0, entropy stays constant. You can see from 4 to 1, entropy of the system stays constant as 1, right? So it's clear that during two isothermal processes, temperature stays constant, 1 to 2 and 3 to 4, but entropy changes. From 1 to 2, entropy increases. From 3 to 4, entropy decreases. From 1 to 2, entropy increases at temperature T2. From 3 to 4, entropy decreases at temperature T1. And during two adiabatic processes, 2 to 3 and 4 to 1, the entropy stays constant, right? But temperature changes. 2 to 3, temperature decreases from T2 to T1, but entropy stays constant at S2. 4 to 1, temperature increases from T1 to T2, but the entropy stays constant at S1, right? So again, But remember, when we are selecting TS diagram, every state of a system corresponds to a point in a TS diagram, and every reversible process corresponds to a curve in this diagram. I repeat, every reversible process corresponds to a curve in this TS diagram. Another thing which I want to mention here, in PV diagram, we know the area under the curve represents the work done, right, by the system or work done on the system, right? And we know the area enclosed within this loop in the PV diagram is net work done by the system, right? Here, what is the area under the curve? You can see area will be just TdS, and that will be the heat put into the system or heat released by the system. So here, area has interpretation of work. So area here corresponds to work. Here, this area corresponds to heat, right? So this area enclosed in this loop is what? I write here capital Q R subscript. That indicates what? It indicates that this area enclosed within this loop represents the net heat put into the system reversibly during this cycle. Here, this area enclosed in this loop represents net work done by the system. Here it represents the net heat put in the system in this reversible process. So this is how we represent equilibrium or thermodynamic states on a TS diagram, and how we represent Carnot cycle in this entropy temperature diagram. So let us move to our next topic. So my next topic is some clarifications for first law of thermodynamics. So I want to make certain clarifications for first law of thermodynamics, because different books use different sign conventions, and most of the times students get confused. So I want to make certain clarifications on first law of thermodynamics. Remember how we put the first law of thermodynamics in the lecture in which we discuss and stated first law of thermodynamics. We said this can be written as dq is equal to du plus dw, right? What is dq? dq is here net heat put into the system. What is du? Change in internal energy. Change in internal energy of the system. Change in internal energy of the system and dW here is work done by the system, right? So dQ is net heat put into the system, du is change in internal energy of the system, dW is work done by the system. And you know, in this first law of thermodynamics, only U is a state function. Heat and work are not state functions, right? This much you know. And we use the convention positive Q means heat put into the system and negative Q means heat rejected by the system. Positive W means work done by the system and negative work means work done on the system. So we said this is simply a statement of conservation of energy, which says if we put some heat into the system, it will be used by the system partly in changing its internal energy and partly in doing work, right? Now, I want to first mention that when we talk of this work here, this work, it has kinds. One kind of work is called expansion work. Second kind of work is called non-expansion work, right? This is one thing which I want to make clear with you. So there can be expansion work, there can be non-expansion work. Expansion work is that work in which the volume of the system changes. So here, uh, volume of the system changes. In non-expansion work, volume stays constant, but still there's work, right? So remember these things. Another thing which I want to mention here, when we write first law of thermodynamics this way, there is an assumption which you must remember. What is that assumption? Assumption is that the system in question, whenever you use first law of thermodynamics, you are applying the first law of thermodynamics to some system. And when you write dq is equal to du plus dw, then assumption within this expression is that we are considering some closed system, not an isolated system. Isolated system can be taken as a special case from this. Closed system means where there is no matter exchange taking place between the system and the surroundings. Heat can exchange between the system and the surroundings. So when we are using this, we are considering some closed system, right? Isolated system is an special case when dq is 0. right? So we are talking of a closed system in general. And it is assumed that in this closed system, no phase changes or chemical reactions are taking place. Very important. In this closed system, no chemical reactions, no chemical reactions or phase changes are taking place. This is very important. I am saying when we are applying first law of thermodynamics to a system, we are considering in general some closed system, and it is assumed or embodied within this expression that in this closed system under consideration, no chemical reactions or phase changes are taking place, right? So you need to uh, remember this forever, right? Another thing, uh, in this expression, when I write positive work is work done by the system, in some books, positive work is used for work done on the system. I mentioned some books, particularly chemistry books. Some books, particularly chemistry books, use this convention. Which convention? Use this convention. That means W is positive means work done on the system, and W is negative means work done by the system, right? So whether, I repeat, some books, particularly chemistry books, use this convention for work. When W is positive, means work is done on the system. When W is negative, means work done by the system. Here I have used which convention? Positive work is work done by the system. Chemistry books use positive work means work done on the system, right? And negative means work done by the system. In my convention, negative means work done on the system, right? So Q, there is no confusion in heat convention because that is uh, mostly used by all books, the same convention that positive heat means heat put into the system, negative heat means heat rejected by the system, right? So I can write this law now this way. If I write it this way, in my convention, du, if I solve for du, I can write du is equal to dq minus dw. Du is equal to dq minus dw. dq minus dw, right? Simple, du is equal to dq minus dw. Now what will be interpretation of this in my convention in which negative work means work done on the system, right? And positive heat means heat put into the system. So in my convention, this means I can change the internal energy of a system by either putting heat into the system or taking heat from the system, or by doing work on it. I can change the internal energy either by heat or by work or by a combination of both, right? Right? Or I can say the internal energy of a system can only be changed by the flow of heat or work across the boundary between the system and the surroundings. Got it? Now, if same equation is written by in according to this convention, it will be written as du is equal to dq plus dw. So again, conclusion is same, that the internal energy of the system can be changed either by heat or work or by a combination of both. Here this plus dw represents work done on the system in this convention. In my convention, negative work means work done on the system. Here positive heat means heat put in the system. Here positive heat means heat put in the system. So whenever you use first law, you need to keep track of these sign conventions, which is very important, and need to remember when we are applying first law of thermodynamics, work can be expansion work, it can be non-expansion work, and similarly, when we apply first law of thermodynamics, uh, we are considering some closed system, and in that closed system, it is assumed that no chemical reactions or phase changes are taking place, right? Another thing which I want to mention is if we look at the microscopic level, our internal energy, which is a state function, it can take on a number of forms. Let me mention. So waved at a microscopic level, at a microscopic level, the internal energy, the internal energy can take on a number of forms, can take on a number of forms, such as the kinetic energy of the molecules, the kinetic energy of the molecules, the potential energy, the potential energy of the constituents of the system, of the constituents of the system, the internal energy stored in the form of the internal energy stored in the form of molecular vibrations and rotations. Internal energy is stored in the form of molecular vibrations and rotations. Another, the internal energy stored, the internal energy stored in the form of chemical bonds that can be released through a chemical reaction, that can be released, bonds that can be released through a chemical reaction, through a chemical reaction. The total of all these forms of energy for the system of interest is given by the internal energy U. I repeat, the total of all these forms of energy for the system of interest is given by the internal energy, which we represent by the symbol U. Right? This is all for today. Thank you. God bless you. Assalamu alaikum.